untrusted, and he's going to talk on demonstrating arbitrarily weak entanglement using untrusted measurement devices.
Good. So, good morning, and I guess you've already heard about this subject 2 times before in this very conference. Actually, on the tutorial session, I've seen that Professor Guru Prasad Kha has talked about this question of using quantum input scenarios to distinguish all entangled states. And actually, there was a poster yesterday by Manik Banik on the role of free will in this kind of scenarios. So I'm glad to be at this conference and present this subject in depth. Actually, I'm Denis Rosset. I come from the University of Geneva. I will talk about using measurement device independent entanglement witnesses to distinguish any entangled state from the set of separable states. I would like to emphasize that this is a collaboration, and my most important co-author is Cyril Brancière, who is actually in this room. I don't see where exactly. And is the one who contributed to this idea of using this scenario to basically witness entanglement. Also collaborated with my advisor, Professor Nicolas Gisin, and the postdoc who was in our group at the time, Yongshan Liang. I would say I also benefited from discussion with Francesco Buscemi, who first came with this idea of using quantum input in this scenario. And one major point that enabled to construct explicit inequalities came from a discussion with Andreas Winter. So you see that there is a strong link with this conference. The main question is actually, how do we distinguish between quantum resources, such as an entangled state, and classical resources, such as local operation assisted by shared randomness? I'm putting the question of witnessing entanglement in a slightly more general framework. You will see why a bit later. And actually, any separable state you can construct using local operation in shared randomness. So for now, you can think of that as witnessing either quantum resources such as entangled state or separable states. And the extension I will talk about a bit later is actually, you also allow a quantum channel between Alice and Bob, and in the classical world, you also allow classical communication. We'll see how all of this resources will play a role a bit later. The plan of my talk is as follows. First, we will look at 3 ways of how to witness entanglement. Basically, first, standard entanglement witnesses. Then we'll move to how we can use non-locality to witness entanglement. And lastly, I will introduce measurement device independent entanglement witnesses. Then we'll see what are the ingredients that we have to use for MDIs, and then plans for future research. One thing I noticed just about speaking is that if I move my head this side, you don't hear me. If I move my head this side, your amplification, is that right? Is that correct? Maybe I should move the microphone a little bit. Is it better right now? Yes, thank you very much. So let's start with how can we actually witness entanglement? Between distant parties, Alice and Bob, who pretend to share an entangled state, and cheating party that just don't have an entangled state, but will try to simulate the correlation that would arise from this supposed entangled state. So the first way that people use is standard entanglement witnesses. And an entanglement witness is defined as an operator that when the expectation value of that operator is measured on the state rho AB, this entangled state rho AB, the value is negative, whereas this operator gives a non-negative value for all separable states. And how do you actually measure the expectation value of that operator? You perform well-characterized measurement using some local decomposition of this W, and you check that actually this value is negative. What's important here is that you have to trust that the measurement you are doing at Alice's site and Bob's site are trusted or well-characterized. The problem with that is as follows. So geometrically, we can view an entanglement witness as a hyperplane that separates the set of separable state and the set of entangled state. So if we have a state here that's separable, of course, if this witness is correct, violation. What happens is maybe you have some systematic errors in the measurement you perform in the lab, and instead of maybe measuring sigma x, sigma y, sigma z, you have a slight rotation that you don't know, but that are just systematic errors in your measurement process. What will happen is because you construct this W assuming that the measurements are perfect, actually the entanglement witness you will use is this one, and now the state that's separable here will have a negative value, and then you have a false positive. So that's one of the things you have to take care of when you use standard entanglement witnesses. So to summarize, standard entanglement witnesses, they are device dependent in the sense that you have to trust that the measurements you perform are really the ones that are prescribed by the protocol, which is to say that they are sensitive to any systematic error you have in the process, but they will detect all entangled states. Another way to witness entanglement is to use non-locality. It's widely known that there are classes of quantum states that violate Bell inequalities. So what you do is you just use the measurement that would lead to a Bell inequality violation. You perform the Bell test. And what's very good here is that I still have this convention that this dotted line indicates that you have to trust some part of the process. Here you don't. You don't have to trust the measurements. Then you check that the correlation you obtain are non-local. If it's the case, then it means that you have entanglement, because non-locality indicates entanglement in that case. Just as an example, which will be important for the notation a bit later, if you have the singlet state shared between Alice and Bob, and you perform measurement either on sigma x and sigma z in a rotated basis, you can violate the CHSH inequality maximally. And here, actually, the parties Alice and Bob will receive input S and T that are bits, classical bits, that will tell them what measurement to perform. So if I want to say inputs here for the measurement to perform on the shared state. What happened here is that the entangled state will reach, singlet state will reach the maximal value 2 square root of 2, whereas if you only have a separable state or shared randomness, you can only go up to 2. Actually, that's not completely true. Why? Because actually you can cheat here using classical communication. So if you have a scheme like this, where Alice just sends input to Bob, and Bob just computes locally the probability distribution you want both parties to reproduce, and he sends back what Alice should output, then basically you can even simulate a PR box. Which is why when you use non-locality to witness for entanglement, if you want to be really sure, what you have to do is to exclude LUCC, for example, by performing the measurement in a space-like separated way. So to summarize, non-locality is device independent in the sense you don't have to trust the devices. Some entangled states actually violate a Bell inequality, so they can be tested using non-locality. But some entangled states have a local model, so you cannot use this method. And you have to take care of the parties not being able to communicate classically, because you can do simulation here. For example, for the singlet state, we have the Turner-Bacon model with just one classical bit. So now just to introduce the measurement device independent entanglement witnesses, which I will call MDIs from now on. The idea is that you just want to trust state preparation devices. So here in this scenario, Alice and Bob pretend to share the state row AB, and what you do to test these two devices is you provide them with a state that you prepare yourself, and you trust the preparation of that state. You don't trust anything else. And what you will ask Alice and Bob to do is to perform a Bell measurement. I will provide you the details in the second part, just to give you an overview for now. What you do is you prepare a state tau s or omega t from a set of states, and at each time you remember the index of the state you prepared. You collect the measurement result. You look at the probability distribution you got. There will be an inequality later. You check that you have a violation. If you have a violation, it means that rho B is entangled. This is the claim. The claims are that it does not depend on that the measurement devices perform really the measurement you ask them to perform. It will detect all entangled states, including bound entangled states, and you cannot cheat or simulate the correlation using local operation and classical communication.
But if you trust the sources,
yeah.
what is there to check?
Oh, that's a good point. I'll come back to that question in 3 minutes, just after the summary. So these are basically the three ways to check for entanglement, and every time there will be some trade-off between what do you trust? Do you trust everything? Do you trust nothing? So when you trust basically all the measurements you will use standard entanglement witnesses. When you don't trust any devices, you can use non-locality, which led some people to talk about device-independent entanglement witnesses. Maybe you've heard that name, DEW. And here we provide something in the middle where you trust actually local sources, not entangled sources. So tau and omega are not entangled. And they are prepared in an uncorrelated way. That's the key point. But we will come back to that a bit later. So that concluded the first part. Now I want to talk about the ingredients for these MDUs. First, I will explain in detail what are these quantum input scenarios, show you how to construct explicitly an inequality. Then I will prove that this inequality is valid for all classical resources. And then we'll see that you can have a quantum violation. So here just to state that why do we have this assumption that it's easier to trust state proportion devices than measurement devices? It's because actually measurement devices are open to the environment. So it's very easy for someone to send you something that was unexpected, which is why this blinding attack worked actually. You send something that's outside the specification. Here what we assume is that we trust the state preparation, but most importantly, we trust that these devices are not leaking information. Maybe you remember the very talk at this conference, I guess, was about this implementation of BB84, and every time a one was sent, you could hear the power supply buzzing because it drew more power from the power supply. So you don't want actually to have this kind of leakage here and here. This is part of the assumption. Then what you do actually, you ask Alice and Bob, like in a generalization of a Bell scenario, you ask Alice and Bob to perform a measurement using the state that you provide them, this input state, and part of the state they share with the other party. So basically, here what I will do is give Alice the tau OS I prepared, ask Alice to perform a Bell measurement that will be described by this operator, and Alice will perform actually this measurement on the state she received and the state she shared with Bob. And Bob will do the same. And here what are quantum input or quantum instruction is that I can provide quantum state as input along with the description of the measurement the party are supposed to perform. So let's see how this works in practice. First, I want to test an entangled state. So I suppose that the Alice and Bob who pretend to share an entangled state will give me a description of the state that they pretend to share. And the state supposedly lives in some Hilbert space. But I don't assume that it lives. They just pretend that it's in this Hilbert space. And if this state is entangled, there will be an associated entanglement witness. So this operator W, whose expectation value will be negative on rho and non-negative on all separable states. That's just here a mathematical tool. Then I will actually build a set of input state for Alice, a set of input state for Bob that lives in the same Hilbert space as this part here is supposed to be in. This is to be able to do a Bell measurement. The Hilbert spaces have to be compatible. And this set of state here and here have to be tomographically complete such that I can decompose the witness associated to rho using some real coefficient beta st. What I did here is to put some transpose just as a convenience because these are local states that are local to Alice and to Bob. This is not going to change anything about non-negativity of the state. Just convenience for the calculation later. So I decompose this witness on the basis given by tau s and tau t with some coefficient beta st. And I will remember this beta st coefficient because I will use them in the inequality later. Now, what Alice and Bob will give us after they did the measurement is a bit, and the value 1 will indicate success, the value 0 will indicate a failure of the measurement. We'll see exactly what kind of measurement we perform later. then what you do basically is you collect the probability of getting the result, given that you provided the parties, the states, tau s, omega t. So to summarize, what do we have? We have a set of quantum input tau s, a set of quantum input omega t, that we will use to characterize some state rho. Using this set of input state, we have a decomposition of that witness. And now we have two claims. The first claim is that this inequality will be always satisfied by classical resources, in the sense that when I take the probability of having a conclusive answer for both Alice and Bob, and I sum over with the coefficients, the result will be non-negative for classical resources. You say? Yeah. They depend on the description of the state that Alice and Bob pretend to share, of course. Because the witness W will be the witness associated that is able to detect the entanglement in rho. A bit later, I can tell you how to construct an entanglement witness for any entangled state. There is a hierarchy that we can use. But let's come back to that later. Here, just to say, by classical resources, I include shared randomness, but also classical communication. And Andreas Winter last year talked about all the kind of LOCC you can have. Here we say LOCC in the more general sense with unbounded communication and infinite number of rounds, even going to the closure, it does not matter. The second claim is that the inequality will be violated by this and the entangled state. Of course, the entangled state that was used to build that is associated with the witness here. So let's first do the proof for the classical bound. So now we have parties that just pretend to share the state rho, where actually they just have classical resources. Actually, the process of what they will do to obtain the result A and B, given the inputs tau s and omega t, we can view that as a POVM, a joint POVM, where the result PAB given ST will be given just by the measurement of the POVM on this input state. And as you know, there are many, many classes of POVMs. We have a POVM that you can apply by using shared randomness, by using classical communication, but just one way. You have all the variants of LOCC. And I said that I acknowledge discussion with Andreas Winter. Actually, what he told me is that if you can try, don't try to characterize LOCC. It's too complicated. Just try to go to separable measurement. And that's what I did for this proof. So what if the POVM is separable, then actually pi 1, 1 will be some convex combination of product operators A1 and B1k, where these operators are non-negative. And this is the key point. Now what we do, we will introduce this expression over there to compute P11 given ST. So I have my inputs over there. I have the POVM on the right. Well, I just play a trick. I put a transpose here, here, and here. This will not change the value of the trace. And now I include back this P11 given ST in the value of the inequality on beta ST. So because the trace is linear, I can put the sum inside here, the terms that depend on ST. And maybe you recognize actually what this term is about. This term is exactly the decomposition of my witness W that I did before. And now once I've done that, here I have a standard entanglement witness. And the property of that witness is that on separable states, it will give a non-negative value. And now it's a bit of an abuse of the notation, but I can look at these POVM elements here and here as quantum states that are not normalized. And the value of that witness on this sum of non-negative product state is going to be non-negative. So there I prove that the classical bound holds for any type of classical resources, including classical communication. Now, so it's satisfied by LOCC resources. Now what I have to show you is that you can violate this inequality using quantum resources. This is what I will do right now. So now A and B share the state rho. They still receive the input state tau s and omega t. And they have to perform some measurement that where the value 1 is a success. So what do we define as a success? It's actually the projection on the maximally entangled state. And as a maximally entangled state, I just take the state 0, 0, plus 1, 1, plus 2, 2, of course normalized. So let's now see what the value of the computation will be. The probability of getting the result 1, 1, given that I receive the state tau s and omega t. So now I have to put the measurement the POVM element A1 and B1 inside here. And I will use an algebraic trick. And the trick is as follows. If I perform the trace on A tensor B on the maximally entangled state phi d, it's equivalent to doing the trace A B transpose of normalized over D. So what? Yes, but here I'm considering the quantum violation. So what happens here is if I don't do the right measurement, I get no violation. So I can, of course, have false negatives, but I will never get false positive. That's a very good point. So now I apply this algebraic trick twice. What I will get is basically the transpose on the tau and omega states. I still have my rho B on the right. And I guess you can guess what will follow. What will follow is that I will do the sum over the coefficient beta st to get the value of the inequality. And as before, you can recognize what this sum is all about. It's actually, again, W, but now W is evaluated on rho AB, and the value will be negative. This is, of course, assuming that when you perform the experiment, you use the right measurement. But still, if the quantum violation is big enough, you can have a little bit of noise, and you still violate. Just as a remark, what was very surprising for us is that this entanglement witness is insensitive to losses. What happened is, what's important here is the sign of the inequality. Whatever you, above 0 or below 0. What happens is, if you don't receive the shared state, you just output 0. You say, I failed to project. And for the quantum violation, this will just decrease the value of the violation, but you will keep the negative sign. Up to a point where basically you have statistical fluctuation, and the negative violation is too small that with the noise that you have, you're not able to say anything. But in principle, you can have arbitrary losses here. What's very good is that the separable bound is still equal to 0. Because all the losses that will happen in the channel here and here cannot depend on the label of the state, ST. They will just be a quantum process. So the proof is still valid if you include what this loss-inducing channel here is doing inside Alice. I'm happy to discuss that in the Q&A afterwards if you want me to comment a bit further. So in summary, what's a MDU? It's an inequality that will be violated by an entangled state, some entangled states. So you tailor the inequality for a particular state. But it will be always satisfied by classical resources. Of course, to be more powerful than non-locality, you have to introduce additional assumption. The assumption are that you trust the state preparation, including the fact that there is no leakage of the index S or T to the environment. And you also assume that there is no quantum channel between A and B. Actually, you can see that if I have violation, of course, a quantum channel is also some kind of quantum resources. So you witness either entanglement or quantum channel, but both are quite interesting. Just as a comparison to non-locality, I'm now looking at qubit Werner state with a visibility between 0 and 1. As you know, Werner states are separable between 0 and 1/3, and they violate the CHS inequality starting from a visibility of 70%. Actually, what they have a local model up to a visibility of 5/12. So here you see that if you use non-locality to prove the entanglement in this state, there are some entangled states here that you're not able to detect using non-locality. And there are some states that you can detect, and there are some states for which not much is really known. People have been trying to close this gap, actually. I haven't shown all the intermediate steps, just the basics one. And actually, one other thing is that when you use non-locality, and you have classical communication between the parties, you can have arbitrary violation of your inequality. Whereas if you use an MDU with this additional assumption, the power of the local model is not is actually the same as a model with classical communication, and the MDU can detect all entangled states for qubit Werner states. So in conclusion, we see that all entangled states in this generalized Bell scenario will exhibit correlation that you cannot simulate even if you have infinite communication. And this provides a way to test the entanglement in all entangled states by these MDUs. And these MDUs, furthermore, are resistant to losses and imperfection in measurements. So with this conclusion, I'd like to maybe look at what's the current and future research. I was extremely happy that some researchers here in India continue this work further along. So Manik Banik showed that actually LOCC cannot simulate the correlation, but if you have lack of measurement independence or lack of free will, actually you can simulate, which saw for the first time that there is a difference between these two assumption, free will, and no classical communication. I'm not thinking of doing experimental tests with experimental groups of these MDUs, either with photon or superconducting qubits. I also have questions that are still open is how to characterize LOSR channel in general, how to deal with imperfection in state preparation. Somehow you can change the set of input that you use in the decomposition. What's the effect of having like 4 or 6 or 10 inputs? Is it better to have more inputs? I don't know. And I'd like also to use this kind of similar witnesses to characterize entanglement-preserving channels, for example, like quantum memories. With this conclusion, I'd like to thank you and expecting some questions.
Thank you. Let's see if I understood. So Alice and Bob are given an entangled state initially, right, and they're told which entangled state is supposed to be, because they need that to decide to manipulate that, right? So from their share of the entangled state, they will each produce a new quantum state, which will be then given to the, and this is done securely, so I mean in the sense that you trust it, and then the quantum state that they prepare from the initial state they're given, that these two quantum states that they prepare, those would be measured by a measurement device that you don't trust.
I'm not so sure I understood your understanding perfectly, so maybe what I should do is rephrase what a MDU is all about, and then we see if we come to an agreement. So maybe I don't like to skip on the slide because we waste a lot of time in the Q&A, but so what we have is we have two parties, Alice and Bob, that pretend, basically you have a vendor that sells you devices, one for Alice, one for Bob, and a source, and it says, okay, these two boxes, they share the state that's in the specification. For example, they share a singlet state. And you want to test that the devices really share this entangled state. So what you do, you have your own devices that produce the local state tau s and the local state omega t, and you use this state. You send this state to Alice, you send tau s to Alice, you send omega t to Bob, and you ask this black box to perform a joint measurement between the state received from the source and the state you provide the box. And you ask Bob to do a joint measurement between the state shared with Alice from the source and the state you produce. And you use the classical result of that measurement to witness the presence of entanglement here. So one thing, this paper is based on a result by Francesco Buscemi, who considered actually transformation of states. So we use that result, but we are not considering at all that Alice and Bob are transforming the state. They're just doing joint measurements.
And from where do these tau s and omega t come?
You say?
These tau s and omega t, they must be prepared by a trusted source?
Yeah.
But they are entangled, right? Tau s and omega t are entangled.
No, they are not.
No, they're not.
They are local states. For example, maybe I need to give a concrete example, which I will do now. Suppose Alice and Bob share a singlet state. What I can do is to produce locally using my own state preparation device, the tomographic state plus x minus x plus y minus y plus z minus z, and I send one of these 6 states at random to Alice. I send one of these 6 states at random to Bob, and I as the experimentalist, I keep track of which state I sent to Alice and which state I sent to Bob, but Alice and Bob don't know which state they received. That's the key.
And then they make a joint measurement between what you send them and what they have,
Yeah.
give one bit output, one classical bit output.
Exactly.
And that is what's tested.
Yeah. I thank you for the question
Yeah.
because I think that
No, it's very clear for me
it's
now.
the same question.
Yes.
I guess I was not that clear at that point. It's very good that I answer everyone now.
Thank you.
Yeah.
So the question is slightly beyond your scope of this lecture, but take the Warner state when it is this weight is less than 5/12, then all measurements can be simulated by LOCC.
Can you just repeat the
For Warner state, if the weight of this singlet is less than 5/12, as you showed,
Yeah.
it can be simulated by local. I mean, just local randomness.
Exactly.
Yeah.
Exactly. Maybe I should come to that slide. Yes, this one.
So my question is, do you think that this result just tells that it is impossible to draw a demarcating line between separable and entangled state by classical input and classical output on both sides?
I think if you stay in the framework of violation of Bell inequalities, because in all this regime we have a local model for all possible POVM,
Yeah.
it means that whatever the correlation I have to reproduce in this regime using an entangled state, I can also do that by LOSR. Which means using just non-locality, it's impossible to draw a line here. You have to draw the line somewhere here. But this is not like this is a lower bound on this local model. Maybe we have a model here or here, we don't know. But we know for sure we have a model up until there, which means that this state here are entangled, but they will never violate a Bell inequality.
But I am asking this question because there is suggestion for some sequence of measurements sometimes reveals non-locality.
Actually, what you can do is you have all the business of activating non-locality, which, for example, is instead of just doing the measurement on one state, you do the measurement on several copies of the state, or you use an additional state that's not able to violate a Bell inequality in addition, and you do joint measurements. And this will all be processes with classical inputs and outputs, but you introduce, you don't do single copy measurement, for example. There is a lot of these results, and some of them are mentioned in the introduction of the NJP reference. So I'm happy to discuss that over lunch if you want.
Yeah.
So you said that even with infinite classical communication, one cannot simulate, right, this kind of
Right.
things. And if we have, instead of quantum inputs, if we have classical inputs,
the measurement and the disturbance you introduce in the state. And because you don't know around which axis the state will be produced, you have to guess, and you don't know when you introduce noise in the process. Yes, yes, because I have at least 3 linearly independent states. Actually, what you can show is that if you only have two states for qubits, there is no entanglement witness that can be decomposed over just 2 states.
Okay, let's thank the speaker again.
Thank you.